So we have estimated confidence intervals for the mean and the proportion, and now we're going to do it for the standard deviation and variance. And we're going to use what's called a Chi-square distribution. This is another Greek letter. It's called chi, so Chi-square. And in this case, we have independent simple random samples of the same size, and we're calculating their sample variances from a normally distributed population with a variance sigma squared. So remember, sample gets the S, sigma for the population. The formula for chi-squared is n-1. This is related to the degrees of freedom. And then here is basically a ratio between the sample variance and the population variance. Note in the diagram here that the distribution is not symmetrical, though it does become more so the larger n is, the larger the degrees of freedom are. The chi-square values can be 0 or positive, but there are no negative chi-square values. Again, it's chi-square, so all positive. The chi-square distribution is different for each number of degrees of freedom. So in this sense, it's similar to an earlier table that we had for T distribution, in which all of those were different for each degrees of freedom. Now, in this particular case, when we want to do a confidence interval, we cannot do what we have done in all our previous examples with mean and proportion. We cannot do something like this. So there is no margin of error equation for this. And that has to do with the fact that it's not symmetrical. We have to do separate calculations of the upper and lower limits have to be performed using the chi-squared for the leftmost critical value, and notice the little L for the left, and the chi-squared R for the rightmost critical value. The confidence interval becomes this. So we have the chi-squared on the right side and the chi-squared on the left side. And then we are going to use table 6 to find out chi-squared R and chi-squared L values. If we want to do the standard deviation instead of the variance, we would take the square root of each value to estimate the standard deviation instead of the variance. The chi-square values can be found in table 6. And again, it's another table that's in the back of your book. So, if we want to get values from table 6, let me show you what table 6 looks like in the back of your book. So there is this little pull-out that you can use for your chi-square distributions. So one of the things to note here is every time you have a certain confidence level, you're going to create 2 columns on this table. Basically a left column and a right column is what you're going to pick. So the critical values, the chi-squared in the body of the table, correspond to an area given in the top row of the table. Those areas in the top row are cumulative areas to the right. So please note how this is opposite of the z-score stuff, which was always to the left. These are cumulative areas to the right and not to the left as they were in table 4 for z-scores. So the area for the rightmost chi-square value could simply be read from the table, but the area for the leftmost chi-square value would need to be subtracted from 1 first before using the table. So, for example, if we have a confidence level of 95%, again, remember the 95% is in the middle. So that means there's 5% split into the left tail and right tails of the distribution. So, what we would have to do with our table then, okay, is for the 0.025, okay, so we have 0.025, so that's going to be one of our column headings. The other one is going to be 0.975. And again, these are notice in the picture, areas to the right. Okay, and so what we have to do is, those are the two columns we will pick, the 0.975 and the 0.025, and then we have to pick whichever row is the appropriate row. Now, if the degrees of freedom gets really huge, notice that it starts skipping, and so in that case you would use the closest row. So again, just to go back to the directions here, for example, a confidence level of 95% would mean an area 0.025 in the right tail, which would mean using the column with 0.025 at the top. And so that was this one here with the 0.025 at the top. Okay, but for the left tail area, we don't use 0.025. We have to use instead 0.975, which was 1 minus, or 1 subtract the 0.025. And that's how we got that one, and so that becomes our other column heading. If we had a 99%, for example, confidence level, well, that leaves 1% on the outsides. Split that in half, that's 0.005, so we would use 0.005 for the right side and use 0.995 for the left side. So it's always going to be in pairs, and the two numbers are always going to add up to 1 when you're done. And again, the actual row we use will depend on the degrees of freedom, and once we have our values, when rounding, we want to use one more decimal place than was used by the original data set. So, a little bit confusing, I know, different table, but let's go ahead and look at an example here, and that will help. So, we want a simple random sample of 22 IQ scores is obtained with a standard deviation of 14.3. Construct a 95% confidence interval estimate of sigma. So, 22 scores, n is 22, so the degrees of freedom is 21. So that means we're going to look at row 21. 95%, so on table 6, we're going to use the 0.975 on the left and the 0.025 on the right. Those are the two column headings that we're going to use. So let's go take a look at our table. So if we look at the 0.975 and go down to row 21, notice that we have 10.283. And then if we go across to the 0.025, again, same row, row 21, we have 0.025 at the head, 21 here, so we get 35.479. And those become our two chi-squared values. Now we can plug them into our formula for chi-squared. Again, n minus 1, that's the degrees of freedom, so 22 minus 1, that's 21. The s, that was the standard deviation for the sample. Don't forget to square it, because really this is using the variance here, not the standard deviation. And then here are our two chi-square scores. Now, it can be a little bit confusing to, like, you know, well, which one goes where? The easiest thing to keep straight is the bigger one is always going to go on the left. Okay, so 35.479, 10.283, put the bigger one on the left. The numerator portions are the same for both of them. So if I divide by a bigger number, the overall value will be smaller on the left side. The overall value will be bigger on the right side if I use the smaller one. So again, it can be confusing to keep straight left and right. What does that mean? But you're going to always do two column headings. One of the column headings is going to match half of the difference between the confidence interval and 1. So 1 minus 0.95 would be 0.05. Half of 0.05 is 0.025. That gives me one of them. The other one is going to match 1 minus that, gave me the other one. So those are my two column headings. And again, if you get confused about which one goes where, bigger one on the left, smaller one on the right. So we go ahead, multiply, divide. Here's what we get for the variance. Square root all three spots, and there's our answer for the standard deviation. So we have built a confidence interval for the standard deviation. It's going from 11 to just over 20. Now, one of the things it's really easy to make a mistake on is you got to go back to what does the question want. This question wanted an interval estimate of sigma. So I had to square root everybody. Really easy thing to forget. Okay, another question might have wanted a confidence interval estimate of the variance. Then that would have been my answer. So you have to make sure, based on whatever's going on in the question, that you're actually answering that question. All right, so that's one example. Let's look at a second one. Again, you pretty much end up doing the same thing every time for these. It's just a question of what was the confidence interval, and what row am I going to be having to look at based on the sample size. So here we have a simple random sample of 50 earthquake magnitudes, has a standard deviation of 0.587. We want a 95% confidence interval estimate of sigma. So in this case, n is 50, so that means the degrees of freedom is 49. Now if we look at the table, 49, there is no 49. We would use row 50. That would be the closest one. So the table headings, just like before, 0.975, 0.025. We get different values because now we're looking at row 50 instead of row 21. That's what we looked at before. So the degrees of freedom will change what these two values are. We plug everything in to our equation, go ahead and multiply and divide, and we end up with our variance is between 0.2364 and 0.5218, and square rooting all three spots. Our standard deviation is between 0.486 and 0.722. And so that is how you construct confidence intervals for variance or the standard deviation. And that completes Chapter 6.